Thank you, sir.
Amit, once again, let us move to the next talk.
Th-
Contributed
th-
talk, cellular automata based model for finding minimum spanning tree in wireless sensor networks by Parijat and Debopriya Barman.
Thank you, sir. Should I close my
Yes, yes,
sharing?
please.
Yes.
Please.
Thank you. Thank you. Thank you.
Well, thank you, and thank you very much, Ovik sir. So, should I start sharing my screen? I'm Parijat Sen here.
Yes, yes, please.
I hope my screen is visible right now.
Yes,
My
visible.
screen is my yeah.
Yes, yes.
So, first of all, thanks a lot for giving me this opportunity. And before starting my talk, I just need to say sorry that my pronunciation might not be good. I had sound problems, so please take a pardon. So without wasting any further time, let's start. So today we are going to talk about our work based on cellular automaton based model for finding the as standing wireless as it is written in the title itself. So let's get into it then. So what is the main problem or what is the object we are trying to work on in this project? So the idea is, as we all know, in the whole the conference itself, we are aware that various sectors of computation cellular automatas are used, and what various computation problems are also solved. So now we are trying to check that whether common computation problem like minimum sanity can also be used in wireless sensor network, because you, as we all know, in wireless sensor one of the key factors is to maintain the information on the ID network throughout the network. So that is the primary objective of the work, as it says in the Serotonin, to explore how wireless sensor and accelerometer can be useful together for solving the computational problems. So this is the basic skin of introduction. What is accelerometer? The basic definition, but I don't think we need to discuss about anything more, as it has been discussed many times in this whole conference already. So yeah. So why we are so interested about talking in the wireless sensor network, as we are constantly witnessing how each and every day wireless sensor networks are being used in various sectors, in whether it is monitoring or is battlefield surveillance or in biotechnology or condition monitoring, in each and every sectors of it. What the problem is, wireless sensor network is due to some design challenges like energy efficiency as well as the data, as the memory constraints are there, so and the operational constraints are there, so it sometimes becomes hard to perform existing cluster based works, cluster based methods or centralized operations method in wireless sensor networks. So if we look at the existing works what are already been done, one of the most famous algorithm for finding the MST in distributed network is the Ghs algorithm, which talks about how we can join the different fragments and in order to make a minimum spanning tree, and it is quite famous. But one problem with GHS algorithm was that it had an issue where before before merging more than one fragment, it has to attain a level of maturity, or other than the fragments we couldn't join the fragment. So in 1986 the level A came up with a improvement where we didn't have to wait until and unless both the fragments match their level, or in simple words the height of the subtree, in order to join two small fragments when we are making a bigger linear spanning tree. And so other than this, not many distributed works are there, although in 2015 the Sudami work was done in heterogeneous sensor network, but it was simply using cluster-based basically network where centralized operations were used. And in disadvantage in 2018, basically they used some acknowledgement messages in the Ghs algorithm itself for solving in wireless sensor networks. So other than that, there's not much distributed algorithms and in the wireless sensor networks for finding universality, and there's no such work in the field of cellular automata regarding this. So what we are trying here is we have two phases in our work, two parts. One is to maintain a 2D grid like regular grid structure like wireless sensor network, and then to implementing that our cellular autonomous algorithm in that particular regular grid sensor network. So in our wireless sensor network, we are assuming that as we have a bigger grids, so we will be having, in the further slides I will also discuss in detail, that a node will have in general 4 neighbors, as you can see in the slide itself: west, north, east, and south. So in that way, a node will behave like a grid, and for maintaining the 2D grid structure, we will use the angle of arrival method and the signal strength. So if in a zone there's more than one active node, we'll try that in one zone at any given point, one node will work as a cluster head and other nodes will be in a sleep state. So let us see how the cellular automaton computation works. So in the cellular automaton model, we are using a 2D non-uniform finite cellular automaton, which will find the minimal sanity for unique weighted edge 2D grid graph, just as it was in case of GHS algorithm also. And we are using the for the cellular automaton m cross n grid graph. We are representing 2 by 2 m minus 1 into 2 n minus 1 cells. So in the cellular automaton, for representing the nodes and the edges for both, the same cells are used, but for the nodes cells there will be 10 possible states, while for the edge cells, the cells which represent the edge node edge, we will be using 3 possible states. As you can see in the state diagram, for a node can be, this will be easier for me to discuss. So if we see here, we have a initial grid graph, and this is the configuration how the cellular in the cellular automata configuration this grid graph will look like. So if we represent the grid graph, that as you can see, here is a node, and in between these two nodes there is an edge with cost of 10. So here in the configuration, we are using initially this node as E10 and the other nodes as N nodes. So basically, and all other nodes, all other cells of the configuration are represented at V, which is the redundant state. And all this N infinity, these are our initial state. Look, if I can go back to the previous slide, then it will be easier to understand that at first, each and every nodes are in initial state, which is nothing but N infinity. And from there, in the next state, each and every node gets to know the information of the minimum. As you can see, the node in 7.3, it has 2 surrounding minimum edges, one with cost 10, one with cost 12. But in the next, after the generation 1, the value becomes N10. So, and that happens for each and every node. So basically, in the first generation, what we are trying to achieve is that every node updates its value with the minimal outgoing edge it has among all its neighbors. and we are calling that state as disjoint state. And from there, the the configuration, the evolution starts in order to reach the search state, which is nothing but where a searching will be going on in a fragment. If suppose we have a tree, then in a, let me, yeah, it will be much more easier to understand. If there is a P10 and F10, and so basically these two nodes are connected and part of a tree, already they are joined. So when we have already a fragment, in order to add another node to the fragment, we have to understand what is the minimum outgoing edge from that subtree. So for that, we will be doing a search operation in that particular fragment, and the whole process will run simultaneously for all the existing fragments at that point of time. So this we are calling as search state. And once we acknowledge that the minimum value, then the whole process, then the value will be searched, the value will be returned to the root node, and the search it will after the search return is after the return, during the returning process, the minimum value, it is called search return set. And then we can go to the final state also, which is nothing but when the search is complete and we know that which node has to connect it through the neighbor node. So that is the whole purpose. As you can see here, this node is F12, which is why it is in F12. It says in order to represent that it has a minimum outgoing edge which is 12, and this is that particular node which has among that all the nodes in that fragment who has that corresponding minimum outgoing edge. So that other fragment can also understand it, and the nodes can be joined. So in this way, the whole transition works. And the cellular automaton, so this is the basic cellular automaton algorithm we'll be using. Now let's move on to the second part of our work, which is how we are using it in the wireless sensor network. So first thing we have to do is to maintain a grid structure, because when we deploy the sensor nodes, we most commonly use a randomly the deployment method. So when we deploy nodes in a random manner, our target will be to use the received RSSI, basically received signal strength indicator, to understand what are the signal strength of its corresponding neighbor nodes. And if in a zone, suppose here, as you can see in this picture, one node has higher signal levels than the other node in that cluster zone, this node will not be used for creating the MST, and we will just use one node which has the highest signal strength or the energy to make the MST. So this will help us in both the way. One, we will be able to make a grid-like structure, and also so that we can apply the cellular automaton algorithm. And more importantly, as you can see, we will see in the upcoming slides, as we are not using redundant nodes while making the tree, it will help us to use minimum number of nodes at one certain point in time, and other nodes we can keep in sleep state. So later on, when we have to use when the already used nodes energy level becomes low, we can use the other nodes for our benefit, and it itself will help in getting a more coverage and more lifetime of the network. So as you can see here, you can use the angle of arrival method for understanding the neighbors and the messages, how its neighbors are performing. And if we see the simulation results that we have have achieved that we are, in case of we have checked it for deploying 40, 50 and 60 and 70 nodes respectively, that if we are using 40 nodes in the initial phase, but in order to, while we are creating the MST, on an average the mean is 14.2, and you can see for when we are using 50 nodes the average is 15. So basically we are saving more number of nodes at one given instant time with, and we are getting rid of the redundancy which otherwise would have you have to use while forming the network, and that in return will help us gaining more lifetime of the wireless sensor network, which is a key factor in any existing wireless network, because they don't have enough energy levels and they have limited lifetime. And as you can, if you can look at the generation of the how that it is working, this then if we pick these nodes as the cluster heads in the generation one, then as you can see, as at first also I was talking, at first all the nodes which has, if basically as you can see 116, these two edges are already connected in the first generation. So why? Because both the nodes have one as the minimum edge. The same is applicable for these two also. 16 is the minimum outgoing edge weight for both the nodes. So in first generation, all those possible nodes will get connected where both the nodes have same edge weight as the minimum edge, and consequently the tree will grow. And as you can see here, although we have there are more trees, but they are still growing. And now on, as you can see on generation 12, this two node subtree, which was earlier only having a single edge weight with one edge value 1, it has now added one more node to the subtree with a edge of 7. So this way the fragment gets bigger and bigger in order to achieve the final configuration where we have the minimal spanning tree. But as you can see, all the nodes which are connected to the minimal spanning tree will be active in the initial configuration, but the all other existing nodes we can put it in sleep state. So that's how we can actually use this. We have used our approach in order to achieve the minimal spanning tree and reduce the redundancy, and basically not using all the existing nodes at one go, but using only the nodes which are necessary in the initial state. So now let's we are come to the this info why we are so interested about working in this, because as you all know, the wireless sensor network has its own set of limitations, design limitations, as I have already mentioned, the computational limitations, energy related limitations, power limitations. And one of the most important problem is that in all existing approaches, every node has to maintain an information of every node, node ID, or in Ghs algorithms or in level, they have to use the node ID and level of it. You have to mention the level and hierarchy of each and every node. Unless and until you maintain all those information, you can't join the fragments. But in this approach, we are not bound to manage all those informations. And more importantly, so that will help in return reducing the energy consumption of the wireless network and increasing the lifetime of the wireless network in return. So now if you do at the future improvement, as you can see that here we are using 2D cellular automata. We are what we where we are using 4 neighbors, but in case in future you might also be able to use hexagonal cellular automatons also. We can, so which can even be more impactful and useful for the wireless sensor networks. And as a conclusion, and I would like to conclude by saying the fact that we are able to understand how we can use cellular, we can even use cellular automata algorithms also in practical computational problems like in wireless sensor network for one of the most common computational problems like MST, like nothing more common like than MST can be there. So if we can solve these kind of computational problems, we might be able to solve more and more problems, which also be useful for the wireless sensor network because it suits the basic limitations of the wireless sensor and also the cellular automata, the basic design of it. So yeah, thanks a lot for giving me this opportunity, and that's it from my side. And if you have any queries, I'll be happy to answer.
Thank you, Parijat, for your presentation. Now it's open to the audience. We have about 10 minutes time to discuss on this paper.
Yes, Parijat.
Yes, sir.
I have, you have tackled with the one problem. The approach you have taken, by that approach, you have solved one problem, right?
Yes.
Other graph theoretic problems or other problems which are pertinent to this domain, wireless sensor network. Do you have any plan? I mean, can you solve those problems by the same setting?
Yeah, actually, I was really thinking about one more important thing is single source shortest path problem. As we all know, single source shortest path based routing protocols are very common in wireless sensor network, and these are quite commonly used in wireless sensor network because in wireless sensor network, there's a very common aspect of sync for the collection of data from the environment and that passing on the data to the sync node.
Oh.
So basically, if we look at it from that perspective, it very much matches with the single source algorithm. So we can really, it can be very much useful if we can try to solve the single source shortest path problem in wireless sensor networks.
Okay.
In future.
Okay. And what is the state complexity of your scheme? How many number of states?
Well, we have 10, basically 10 states here for the nodes.
Okay.
Node cells, and for edges only 3 states.
Okay. Thank you.
I have a question, Parijat.
Yeah.
What is the time complexity of your scheme? How much time it's needed to run out? Tell me.
Well, first of all, I think I want to add to with Sumit that what is the problem size? How have you chosen what is the problem size in this case?
Well, in this case, like basically, I have randomly used the like 50 or 60 or 70 nodes and checked it for at least like 100, let's say 70 to 80 variations, how it is working, and that's how it works. And if I, yes,
variation means?
yes, sir, please. I mean, how basically when we are deploying the nodes in the grid region, it can basically
how many
does
the number of grids play a role here?
No, not really. I mean,
in the problem
yeah, I
size?
mean, not really is not that. Yeah, it does. Basically, in simple words, if the number of, basically the whole idea is, as we are using, trying to avoid use one node per grid. So if the number of grids are more, obviously the more active nodes will be at one point in given in time. The number of active nodes will be much higher, and if the sensor nodes are basically, if I can go to the, yeah, so as you can see here, if my nodes are not well dispersed, if I deploy the nodes in a manner where most of the grid is not covered, then it can be a problem, but otherwise it will not depend.
Okay, now come down to the time complexity issue that has asked.
Well, the time complexity I haven't calculated, unfortunately.
Generally, what is the time complexity for minimum spanning tree? Whether you are getting similar thing here?
I mean, I think it is definitely less than n square, because the one of the key approach is same as like in the Ghs algorithm also, as we are
N square
in the
where
initial
n
state.
is?
I mean, n is basically the number of like the, I mean, to enter the message complexity here when I'm saying basically
Number of
the
edges?
when no, not edges, basically the message, whenever the messages are message complexity, when I'm talking.
Okay, continue.
No, basically the time for MST, the time complexity is m log n actually, where m is the message and n is the number of nodes. And I have a specific question, the space complexity. That means you have to store all the nodes, na?
Yes.
So how much space complexity you needed?
Well, so I haven't calculated it.
I think he is the storing. Sumit, what you have asked, I think he is the storing. So
Yeah, he stored the nodes, na?
no, that is the during simulation, but in the proposal, maybe what he has said, say one node will calculate depending on its neighbors, and the rule is there.
No, basically now one the when one node is saving that is not much to store basically. If I'm talking about this node, this has only the information of its current state. It doesn't have to consider all the other states of that particular node. So for each and every number of nodes that we have in active pointer time, basically not more than that particular instance of time, all the states of that particular node, and nothing more than that we have to store at any point in time. No.
That means you have stored
Because-
the information about nodes, na? So
Yes,
suppose in a
or
grid,
from that particular generation.
suppose in a grid
Yes.
there is n nodes. That means how much space
Yes,
you
yes.
need?
Yeah, obviously linear, because all we have to know store the in the previous generation, the current generation values, and nothing else. So that is obviously linear.
That means n number of array can solve it. Okay.
Yes, absolutely. Yes.
And is there is that means can we apply into the longest path problem? Like it's
Yes, definitely. I mean, for longest path problem, yeah, I guess so. Because if for linear certainty, you can for longest also, yeah.
no,
Definitely.
that is the two other. Okay. Thank you, Parijat. Thank you. Nice talk.
So, any other question? We have about 3 minutes. Then I think we can move to the next